So what is oscillation? Well, let's consider a case of something that will oscillate over time. So let's look at a very simple setup. Suppose I have a floor sort of like that, and on the floor will be a block, and it will have some mass of m, and attached to that block will be a spring. I know this is a very bad way of drawing a spring, but just bear with me, right? Because we can't really draw. Physicists, we can't draw. But attached to that mass is a spring, and the spring will have a spring constant, or basically like how stiff the spring is, and it will be equal to k, right? Now, the question is, suppose the mass right here, we call this position x equals 0, right? And it can move along, well, this plane, basically. It could maybe be here, which is x equals to another number, a positive number, and maybe this be equal x be some negative number, for example, right? Now, the question is, what will the motion of that mass attached to the spring look like, assuming like no frictions, no air resistance, those sort of things? Well, how do we model this system? Well, from Hooke's law, we know that the spring, when compressed or extended, will have a force. And so we can write that force down. So the force, or F, will be equal to, in this case, because it's a spring, it will be equal to kx, which means it will be proportional to the distance, or this case will be like how much the mass slides along this direction. But if the mass is, for example, here, if the mass is positive, or if the mass is at a positive displacement, then the force will be pushing it in that direction, in the negative direction. If we call this the positive direction, this is a negative direction. If the mass is at a positive position, its force from the spring will be in the negative direction, and so we need a negative sign there. Now, we can go look at Newton's laws of motion, because we have force, and because this is classical mechanics, we can look at Newton's laws of motion, in particular the second law of motion. We know that the force F will be equal to mass times acceleration, which in this case, the force, there'll be only one force, which is minus kx. But now we also know that acceleration turns out to be the second derivative of position. That is just a fact about calculus. That's basically how acceleration is defined. So we can write that out in a different way, that actually acceleration is the second derivative of position with respect to time, like that, right? And this will be equal to minus kx. And then I can move everything to one side, like so, plus kx equal to 0, right? And so now we have a strange looking expression, and we don't know how to solve it. Luckily, I'll skip the way that we can solve this equation, and it turns out that we can show that x, as a function of time, will be in the form of some constant multiplied by the cosine of the square root of k over m times time, that's a t, plus another constant like that. This we can simplify. Rather than writing it as square root k over m, we can define another variable called omega, and that will be equal to the square root of k over m, like that. And so now we have a function that describes the position of this block over time. We can plot it out and see what it looks like, right? If we take this graph and we plot it, I'll plot it in a different color. It can look something like this, right? It's a cosine graph, so it will have like this cosine shape. So, well, what can we get out of this equation? Well, you can see that, well, the graph, for example, here, this will be in the time direction, this will be in the position. And so basically what we can see is that this block over time will move back and forth, right? Because as time goes along, x goes back and forth like a cosine curve. And this is basically what oscillation is. Now we can look deeper into some of the coefficients in here, in particular that, and that. This here, the A, is what we call the amplitude. Basically, it is this height. It is basically the furthest that the block can go. What is the largest x that the block can be? Sometimes people write it as x naught because, well, it's a bit more informative and shows that it's related to x. This is what we call the phase angle. It's basically how much this curve shifts along in the time direction. If the curve has a different, well, this letter is called phi. If it has a different phi, no, actually, no, it's not called phi. No, it is called phi. It is called phi. If it has a different phi, for example, the curve might be shifted here, for example, right? This is a more important term that we can talk about because it actually comes from the variables that we have in the equation, is what we call the angular frequency or the angular velocity. And basically, it has to do with how much the curve is squashed. With a different value of omega, if you change the spring constant or the mass, your curve that you might get might look more squished, might look something like that. If this term is larger, then the curve is more squished, or basically oscillates quicker over time. So this sort of affects how quickly the spring oscillates over time. And so basically, just from this simple equation, just from a simple force, you can get out a motion which is oscillating over time, which is pretty cool. But we can go even cooler, and this is where the maths is going to get a bit more interesting. So now suppose I just don't have this spring. I have another machine, which I'll actually draw in pink just because. And this machine is attached to the mass that we have. And this machine basically has a rod that moves back and forth. And basically it's pushing the mass back and forth. And for the sake of simplicity, let's assume that the force that this machine is applying on the mass will be, well, sinusoidal, or basically will oscillate over time as well. And so we'll assume that the force here, as a function of time, will be equal to some amplitude force, some highest force, and cosine of some frequency, this term, multiplied by time, like that. So now we have an extra force acting upon the mass. The question is, what will x of t, this bit here, look like for this case? Well, let's consider it. I'm going to use pink. I'm not sure we can see pink. Again, start with Newton's second law of motion, F equals ma. And I'll just write directly that a is actually the second derivative of position, like that. Now, what forces do we have? Well, the first force, again, will still be the force from the spring, so minus kx. But now we have the extra force coming from this machine. And that will just go right into the equation like such. This force here is the force from that thing, right? So the question is now, I can solve this equation, right? So now if I rewrite this equation here, you will look like this, F naught cos of that. Now again, this is a really complicated equation. I don't really want to bore you on how to solve it. You can go check it out yourself. But it turns out that the solution, x of t, the solution, will be in the form of, it will have a term similar to this. So a cos of, I'll write it as omega, but omega is that, just remember that, t plus this term. But now there will be an extra term at the end, and that term will look like f over m, all divided by omega squared minus that term squared, like such. Oh, and of course there will be an oscillation term as, actually it's that term like that as well. And also that is actually f naught, like so. So now the expression looks a bit more complicated, but it still has like the oscillations from before. So as you can see, this bit here is just the oscillation from that. The reason that this term looks exactly the same is just a mathematical sort of technicality, which I won't get into. But the more interesting term, I think, is going to be the term that appears on the right-hand side, which is this term here. So basically this term is just another oscillation, but the oscillation will follow this. It will have a frequency equal to the frequency of the force being applied upon it. But the more interesting thing that I want to point out is the amplitude of this oscillation. Because remember, this is an oscillation. This second term is still an oscillation, but the oscillation will have a different magnitude. And this magnitude here depends on the frequency, which is this number here, and it will depend on the frequency of the applied force as well. So actually, let's take a look at what this amplitude is, because if this is an oscillation, then that means this will sort of also be following this term. We'll also go back and forth with this frequency equal to the frequency of the applied force, but the amplitude will change depending on what the frequency of the applied force is. So if I draw a graph like that, we'll draw the amplitude of this term. We'll draw this term out on one side, the amplitude of the oscillation, squared minus that squared. And because it's the amplitude, we only care about how much it sort of moves away from the equilibrium point here. We'll put an absolute sign on like that. And we'll go from 0 to whatever the amount of the applied force it is. And it turns out that the graph here actually looks like this. It actually has two lines, and it goes off to infinity at one point, and that point is when the applied force is equal to omega. And you can sort of see why, right? Because if these two terms are equal, then the bottom is 0 and it just tends towards infinity. But physically, what does that mean? That means that if your applied force is equal to this, then the mass will oscillate, well, between infinity, back and forth between infinity, which means a very, a very extreme oscillation with large amplitude. Even if you're like really close, even if you're like right here, the oscillation will give a very large magnitude or a very large amplitude as well. And it turns out that that's an interesting fact about, any oscillations. You can see here that this omega actually only depends on the system itself. It doesn't depend on what the applied force is or how hard we swing it in the beginning. It only depends on K, which is all dependent on the spring, and the M, which is only dependent on the mass. So this is actually a quantity that relates to our mass spring system. It actually turns out that a lot of people will call this the natural frequency. And if your oscillation, if your applied force is equal to the natural frequency, you get this really large swings or this really big oscillations. And this is something that you might have heard of called resonance. Right? In reality, of course, the thing won't swing back and forth between infinity, because usually you'll have like friction stopping it or some other forces. But basically, the condition still holds. The graph maybe will look more like will only go up to a certain point, but there will still be like this maximum amplitude, and that will still correspond to the natural frequency, or when the applied force is equal to natural frequency. And this sort of math is what you do in intermediate mechanics, and it's why it's so much fun.